Hello everyone and welcome to MV Tutors. My name is Tsulu and I'll be going through the topic of work, energy and power in physics. Alright, so that normally forms part of your paper 1. Alright, so let us get started with work. Okay, so here I have a person pushing an object, the direction of motion being from left to right. So yeah, it's in the easterly direction. And I'll write down the equation so that when I explain it in words, it makes sense. Okay, so work, okay, is equal to F, normally the force applied, times D, which is the distance through which the force is applied. So you apply force on a object and that object moves a certain distance. So that, or displacement, so that is D. Okay, and then cos theta. Theta would be the angle, all right, at which, so the force that the person or whatever is pushing or pulling with, okay, so relative to the motion of the object. So if the object is moving east and the force is in the easterly direction, we know that theta is 0. But if the force applied is in a westerly direction, whereas the object is moving east, then the angle would be 180, all right? And if an object is moving to the east, but there's a force applied at 90 degrees, then there won't be any work done, but we'll get to that. So now let us get to define what work is in words. All right, so work is the product of a force parallel to the movement of an object and its displacement. So it's a product of force and its displacement, but in which direction or how is that force applied? It's applied parallel to the movement of an object. So whether it's parallel in an easterly direction or westerly direction, as long as it's parallel. And as you can see here, this force, okay, based on how I drew it, it is parallel to the movement of the object, okay? And work is a scalar quantity, okay? So there's no need to indicate with an arrow there or show direction, okay? So it is a scalar quantity and it is measured in joules, okay? Which is shown as a capital J, all right? Okay. So now, going back to this, okay, let me just choose a different colored pen. Let's say this is a rough surface, okay, that this person is pushing. Let's say they're pushing a box, okay. So if I were to draw a free body diagram of what's happening here, first of all, there's the weight, right, of the object. You can indicate it as W or you could indicate it as Fg, okay. Then there's the normal force, which is always perpendicular to the surface, okay. Then there's the applied force. Okay, so F applied, which is in an easterly direction. And then there's friction, because I did say that it's a rough surface. Okay. And maybe as he's pushing there's also air resistance. So if there's air resistance, it's also acting in the westerly direction. Okay. So that's typically how you'd have your free body diagram, okay? And now going to the next concept of the net work that is done. So the net work done, okay, again looking at your equation, it would be produced by the net forces acting on the object, okay? Again, over the distance with which the object moved times cos theta. So this net force, you get it from your free body diagram, okay? So in this case, looking at my free body diagram, I would note that my net force, okay, I would take first of all east as positive. So I would have my force applied minus my friction force minus the air resistance, okay. And depending on whether there's acceleration or not, because force is equal to mass times acceleration. So if there's no acceleration, if it's moving at constant velocity, you could then say it's equal to 0, okay? But if there is acceleration, then you would have to put in a mass times acceleration there. Then you get your force, your net force, okay? Sorry, actually, you don't need this part. My bad. You don't need this. Now I'm going forward. So sorry about that. So I would say the net force, F net. So yeah, force is applied to it because it's moving in a horizontal direction. I'm only considering horizontal forces. The normal force and the force due to gravity, they will cancel each other out. So your net force, it will be the force applied minus the friction force minus the air resistance. Okay, then whatever you get there, you plug it in here. Then you can get your net force. Okay, now let us talk a bit about positive work. All right, so what happens when you have positive work? Oh gosh, positive work. Okay, basically what it means, if we look again at this image here, the force that you have applied, okay, your force applied, and the motion of your object, they are moving in the same direction. Okay, so positive work, it means that your force applied and displacement of object, or rather, the way your object displaces is in the same direction. So displacement of object, they're in the same direction. Okay, same direction. Okay, and then looking at your equation, work is equal to force times displacement times cos theta. Your angle is going to be 0. Agreed? Okay, because your force is going in that direction and your object is also going in that direction, and there is no angle in between. And if you check on your calculator, cos 0 is 1. Okay, so you just have force times displacement. Now, if you have negative work, okay, that means that your force applied and displacement of the object are in opposite directions. Okay, I'm not going to write the whole thing. I'm just going to say they are in opposite directions. Okay. Yeah. So then, let's say, for example, you have an airplane that is being pulled by tension cords so that it comes to a standstill. Okay, let me attempt to draw an airplane. Let's say you have an airplane there. There are its wings. Okay, the windows there. Okay, it looks like a fish now. But you have tension strings. Okay, let me just use a different color. So you have strings here pulling at it, okay, so that it can come to a standstill. Okay, so we say Ft for tension. All right, so if you have realized, the aircraft is moving in an easterly direction. Okay, so the force that is applied by the engine is allowing this airplane to move east, but the tension cords are going west. Okay, so in that case, the angle between the two would be 180 degrees. So if you look at your equation again, which is FD cos theta. Theta would be 180 degrees. And if you plug that in your calculator, you'll get that it's -1. So the work applied is negative. Okay. Now what happens if you apply a force that is perpendicular to the motion of your object? So you apply a force in this direction and the motion is in that direction. So I'm just going to say V. That direction. Okay, so you agree that the angle in between there is 90 degrees. So again, plugging it in your equation, cos 90. If you plug cos 90 in the calculator, you're going to get 0. So there is no work done if the force applied is perpendicular to the direction of the motion of your object. Okay, so now we're going to come to the last concept of work, which is the work-energy theorem. Okay, so what does it say? It says the net work done on an object is equal to the change in the object's kinetic energy. Okay, so I've written the equation there. I don't know how you guys do it at school, but I write my kinetic energy like this. Okay, so energy and then just showing there with a small k that it's kinetic. And basically, if you were to expand it, you know kinetic energy is half mv squared. But now we're going to look at the final one, minus half mv squared initial. All right, if you want to simplify it further, the half and the m, which is the mass of the object, it doesn't change. But what changes is the velocity. So you have your final velocity squared minus your initial velocity squared. And now we're going to go over the concepts of energy, and we're going to end it off with power. Okay guys, so what is energy? Energy is the ability to do work. So you cannot do work without energy, okay? It's required. And looking at energy, there's a concept called the conservative force. Okay, so what is a conservative force? They like asking this question. Give a definition for a conservative or non-conservative force. You need to know the difference between the two. So a conservative force is a force for which work done in moving an object is independent of the path taken. Okay, so those are the key words. Independent of the path taken. All right. And an example for that would be gravitational force. Okay, so for that, it doesn't matter what path you take. Gravity will always be there. It will always act on an object. Okay, another example would be electrostatic forces. Okay, another thing, let me just see what to look at is the elastic force in a spring. Okay, so yeah, elastic force in a spring. So I'll just say springs, elastic force. Okay, so those are the conservative forces. They are independent of the path taken. Now, a non-conservative force, that is a force for which work done in moving an object is dependent on the path taken. Okay, and what comes to mind immediately is the friction force. Okay, it does depend on the path taken because in some parts the friction or coefficient of friction is less, in some is more, but it is dependent on the path taken. All right, whether it's in a straight line or it's meandering, it doesn't matter. It's important. Okay, so you would get your friction force, even air resistance, okay. What can I say? Another one, that example I illustrated with the cables pulling back on the airplane, causing it to stop. So tension in cables as well. Okay, so those are a few examples of non-conservative forces. Now we come to the principle of conservation of mechanical energy. Okay, so that is the total mechanical energy in an isolated system. Okay, so that total mechanical energy in an isolated system, it remains constant. So it means that the external forces acting on the system is zero. By zero, it doesn't mean that there are no forces acting. It just means that the forces that are acting end up cancelling each other out and they are equal to zero. And we illustrate that with this equation. This NC here, it's non-conservative, okay? And we just discussed that non-conservative forces, that could be your friction, it could be your air resistance or the tension in cables. So if you're looking at the total mechanical energy, okay, that would be the change in kinetic energy plus the change in potential energy. Okay, and if I were to just write that out fully, with the change in the change in kinetic energy, I illustrated it before. So it's just half mv squared. But because half and m are constant, I'm just going to write there final velocity squared minus initial velocity squared. And then potential energy, okay? So we've never really spoken about that, but potential energy, it is self-explanatory. It is the potential that an object has. Okay, the energy that, or rather the potential energy an object has. Okay, it has the potential to do a certain thing. Okay, and that is dependent on gravity, actually. So, why am I saying half? It's actually mgh. Yes, so your mass will be the same. The gravity acting on the object will be the same. But the height, I'd say height at the second position minus height at the first position, or height final, height initial. It's really up to you what you prefer. Let me just stick to final minus initial. Okay, so yeah, that is, if they say using the principle of conservation of mechanical energy, they mean this equation over here. All right, and then lastly, what I can say about energy, remember that energy cannot be created or destroyed, but it can be transferred from one object to another, or it can be transferred from one form to another. And we actually see here with kinetic energy and potential energy. If you consider a slide and someone is just sitting there, please excuse my drawings. So here, they have the potential. Okay, so it's at a certain height. So here the person has a potential to move forward, right? So here that is where potential energy actually applies. And as they start moving, potential energy is converted to kinetic energy. Okay, so at this point, your potential energy is at its maximum. And then it keeps decreasing, right? Because the height keeps increasing. So this person goes all the way until they get there at the end. Okay, and yeah, so at that point, just before they stop, their kinetic energy is actually the maximum. So along the line, the potential energy reduces, okay, and it's also converting to kinetic energy, which along the slide, the kinetic energy actually increases. All right, so that's the transferring from one energy type to another. Okay, and then lastly, we talk about power. What is power? Okay, so power, it is the rate at which work is done. Okay, so whenever there's rate, just know that there is a time factor. Okay, so rate, like we said, you can't work without energy, and how good your work is. Basically, if you're working hard at a short space of time, you've got power. Okay, so rate at which work is done. Okay, yeah, so it's the rate at which work is done or energy is transferred. Okay, and that is indicated by this formula here where P. Oh, another thing about power, it is measured in watts. Energy is measured in joules. Okay, energy is also a scalar quantity. So power measured in watts, W, the capital W, it is the rate at which work is done. So it's work over delta T. Okay, and it is measured in watts. Or you could say that is the change in energy over the change in time. Okay, depending on what information they have given you, you'll use whatever equation is applicable. All right, and then, yeah, what am I missing? There's also average power. Okay. Okay, so average power, you get it by multiplying the net force or force acting on an object times the average velocity. Okay, so yeah, if you look at your equation over here, okay, if you're wondering where does force and velocity come from, you have work over delta T. Remember that work is actually force times displacement. I'm not going to put in the cos theta because that really depends on the angle between the force applied and the direction of motion of the object. Okay, and then you have time there. Okay, so the force part we get, right? That's force. And then you have the distance or displacement over delta T. And you know that displacement over time, that's actually velocity. Okay, so that is where that comes from. And that's average because of this delta T here. It's going to be T final minus T initial. So it gives you an average time. Hence, the velocity also has to be average. Okay, so that is still measured in watts. But if you want to put in the individual units, you know that force is in Newton and velocity is in meters per second. Okay, guys, we've covered all the theory, I believe. Now I can go straight to the questions, past papers. Okay, so looking at the 2019 November paper, question 5, that's normally where that section is, work, energy, and power, it's normally question 5. So it says an object of mass 1.8 kilogram slides down a rough curved track. So by rough, I know there is friction. Okay, and passes point A, so there's point A, which is 1.5 meters above the ground. So this thing, I'm supposing it was stationary, and then due to gravity, it starts sliding down. So here I'm already seeing potential energy at its max, and when it reaches the bottom, I see kinetic energy at its max. But anyway, so it is 1.5 meters above the ground, and it's moving at a speed of 0.95. Okay, so it was not stationary. It was already moving at that speed. All right, so the object reaches point B at the bottom of the track at a speed of 4 meters per second. So you see the speed did increase. So your maximum kinetic energy is there at the bottom. All right. Yeah, so let us see what the questions are saying. Okay, so the first one, define the term conservative force. Okay, we spoke about it. You know it by now. Basically, it's when you apply force on an object where work is done, that is independent of the path taken. And we did say examples are gravitational forces or electrostatic forces or force in a spring. All right, so that is 5.1. And then 5.2, name the conservative force acting on the object. Okay, guys, with the examples that I've just said, gravitational, electrostatic, spring and a force, a conservative force acting on that object is definitely gravitational force. Okay, so I'm just going to say Fg, which is a gravitational force. Okay, and 5.3, is mechanical energy conserved as the object slides from point A to point B? Choose yes or no. Give a reason for your answer. Okay, guys, mechanical energy is not conserved in this case. Why? Because we have a force of friction. Okay, so no, because we have a force of friction. Okay, so it's not the kinetic energy before is equal to the kinetic energy after. Okay, or the potential energy before is equal to the potential energy after. Because of friction force, you will lose some of that energy to the force of friction. Okay, and your object will slow down because of the force of friction. So that is why. If it were if it were just a smooth surface, then in that case mechanical energy would be conserved. Okay, 5.4. So it says calculate the gravitational potential energy. Sorry about that. Okay, of the object when it was at point A. Okay, so the formula for that would be, so potential energy is mass in kilogram times gravitational acceleration times the height. And at point A, the height was 1.5, the mass was 1.8. Okay, so 1.5 times 9.8, that's a constant, times, oh sorry, was the okay, the mass was 1.8. The height was 1.5. All right. And then using our calculator, okay, we have 1.8 times 9.8 times 1.5, and that is 26,46. And that would be joules. Remember, energy is measured in joules. All right, now 5.5 says, using energy principles, calculate the work done by friction on the object as it slides from point A to B. Remember, friction is a non-conservative force. And when we were going through the theory, we learned that a non-conservative force is equal to change in kinetic energy plus change in potential energy. All right, so our velocity before, I'm just going to expand this equation, we have half m, right? So velocity final squared minus velocity initial squared, and then we have mg, and then we have height final, height initial. Okay, so we need to go look for the velocities. The velocity initially was 0.95 and finally it was 4. Okay, and then our height was 1.5 initially, but finally it was 0. I hope I remember these numbers. 0.95 and 4. 0.95 before I forget. And the height started off, well, it was 0 at the end, and then it started off as 1.5. Okay, the mass is 1.8, so I'm just going to say 1.8 over 2. And here we have 1.8 times 9.8. Ooh, okay, I squeezed things in, but let us see. Alright, so we have 0.5 times 1.8, and in brackets we have 4 squared minus 0.95 squared, okay, plus 1.8 times 9.8, and then we have in brackets 0 minus 1.5. Okay, and that is equal to negative 12, I'm going to round up to 2 decimal places, 0.87 joules. And yes, because friction is opposing the motion, it has to be negative. All right, and then the last question. All right, so the last question, 5.6, What is the value of the net work done on the object as it slides from point B to C? Remember, net work, we get it by getting the net force and the distance and so forth. But in this case, if you're going to use kinetic energy and potential energy, if you look at this position here and that position there, so the heights are 0, right? So there is no potential energy acting there, it's 0. Okay, because of the height, it's 0. If you look at velocity, what did they say about B and C? Okay, so the object reaches point B at the bottom of the track at that speed. They didn't say anything else. Okay. All right. Oh yes, they did say surface BC in the diagram above is frictionless. Okay, so if it is frictionless, this 4 meters per second at B, it will also be 4 meters per second at C. Okay, yeah. So then also the kinetic energy, guys, is going to be 0 because the final velocity is 4 squared. The initial velocity is 4 squared. So for 1 mark, really you don't have to calculate, but the value of the net work done will be 0 joules because we've seen potential energy is going to be 0, or rather the change in potential energy is 0, and also the change in kinetic energy is 0. So the net work is 0 joules. Okay, so I went ahead and looked for a paper where there's at least something to do with power, so that you can see what kind of questions they would ask concerning power. Okay, so looking at the 2018 paper, the diagram below shows a vehicle with a mass of 1,500 kilograms. Starting from rest, so if it starts from rest, we know that the initial velocity is 0 meters per second. So it starts from rest at point A at the bottom of a rough incline. So rough incline, we know there must be friction force. Point B is 200 meters vertically above the horizontal. Okay, so yeah. Now the total work done by force F that moves the vehicle from point A to B in 90 seconds is that. Okay, so if you were to like draw a free body diagram, you'd know that is your force applied. Okay, and your friction force is acting in that direction, and your normal force of gravity as well as your normal force. Okay, you'd have to put FG in its components, but they're not asking for that, but that was just for extra info. Now they say define the term non-conservative force. Okay, so like we had discussed, it is a force whereby the work done to move an object from one location to another is dependent. So non-conservative forces are dependent on the path taken, but a conservative force is not dependent, so it's independent of the path taken. And an example of a non-conservative force would be friction force, air resistance, tension in the cables, etc. Okay, so we have defined the non-conservative force. Now 5.2, is force F a conservative force? Okay, yes or no? Okay, so this force here, guys, the question to ask yourself, when I apply this force, is it dependent on the path taken or not? I believe it is. It has to be on this exact path, guys. So yeah, it is a conservative. No, it is a non-conservative force. Oh my goodness, now here I am doing wrong things. It is a non-conservative force. Okay, and then they go on to say calculate the average power generated by force F. Remember, average power is equal to force times average velocity. Do we have anything along those lines? Okay, guys, so with the information given, we know that power is equal to work done over delta T, or is equal to the change in energy over delta T, or we have average, which is derived from that equation as well. It would be the force times the average velocity. So depending on what information they've given you, use that. All right, so what have they given us, guys? They've given us the work done, total work done by F, okay, and the time. So I wouldn't take this equation here because this equation is derived from that one, but we have work, so we can just go ahead and use that equation. So the work done is 4,8 times 10 to the power 6 joules, and time is 90 seconds. Okay, so yes, the SI unit for time is seconds. You don't need to convert it to anything. And at the end, you're going to get an answer in watts. Okay, so we have 4,8 times 10 to the power 6 times 10 to the power 6, and we have 90 seconds. So we have 53,333,33 watts. Okay, I would simplify that by saying 53,33 kilowatts. But yeah, that is that, and that concludes our session. So yeah, guys, if there's anything you don't understand and you would like a private session, please do contact us on our website www.nptutors.co.za, or you can WhatsApp us on 076 312 1107, okay, or just comment below if there's something unclear and we will get back to you. Thank you.